In the outer reaches of our solar system, where sunlight arrives weak and golden, there exists a world so impossibly beautiful that it seems crafted from mythology rather than physics. Saturn, the ringed giant, a planet crowned with bands of ice and rock that stretch hundreds of thousands of miles into space, glittering like a celestial ornament suspended in the cosmic dark. From Earth, through even modest telescopes, it appears serene, elegant, almost inviting. Yet this vision of grace conceals a profound truth that challenges everything we imagine about interplanetary travel. Saturn is not merely distant, it is separated from us by a gulf so vast that the very question of reaching it transforms into something far more complex than simple mathematics. How long would it actually take us to reach Saturn? The answer, as we will discover tonight, is not a single number, but a spectrum of possibilities, each one shaped by technology, physics, human endurance, and the invisible architecture of orbital mechanics. Depending on the spacecraft we choose, the trajectory we follow, and the planetary alignments we exploit, the journey could span anywhere from 2 years to nearly a decade. Some proposed technologies could shrink that window dramatically. Others, still theoretical, whisper of futures where Saturn might lie only months away. But between the dream and the reality stretches a landscape of engineering challenges, biological limits, and cosmic patience that few truly comprehend. Tonight, we will traverse that landscape together. We will explore not just how long it takes to reach Saturn, but what that time means. What happens to the human body during years of weightlessness? How do mission planners choreograph intricate dances with Jupiter's gravity to steal momentum from a planet? Why might traveling faster actually yield less scientific reward? And perhaps most intriguingly, when will humanity genuinely attempt to send people, not just robots, into Saturn's golden light? This is not simply a story about distance. It is a meditation on time itself, on the patience required to reach the truly extraordinary, and on the peculiar mathematics of space where the shortest path is rarely a straight line. Saturn waits, turning slowly in the outer solar system, its rings casting shadows across cloud bands that churn with storms larger than Earth. It has been waiting for billions of years. The question is not whether we can reach it, but how long we are willing to journey before we arrive. The answers may surprise you. They surprised us. Because the path to Saturn is paved not just with propulsion and fuel, but with invisible highways carved by gravity, with windows of opportunity that open and close like celestial gates, and with choices that balance speed against survival, ambition against reality. From the chemical rockets that carried Voyager past Saturn in mere years, to the ion drives that pushed Cassini through a 7-year odyssey, to nuclear, concepts that exist only in blueprints and dreams, each technology reshapes our relationship with time and distance in profound ways. Before we drift deeper into the calculations and the physics, into the mission histories and the futures yet unwritten, we want to hear from you. Wherever you are on this pale blue dot we call home, whatever hour finds you listening to these words, take a moment to share your presence with us. Leave a comment below telling us where you're watching from and what time it is in your corner of the world. Perhaps it's deep night and you're drifting towards sleep. Perhaps it's early morning and you're beginning your day with cosmic wonder. Wherever you are, you're part of this journey too, a community of curious minds scattered across continents, united by the question of what lies beyond. Now, settle in. Let your thoughts expand outward. beyond the atmosphere, past the moon, through the asteroid belt, and into the realm where giants dwell. Saturn is waiting, patient and eternal, wearing its rings like a promise. Let's discover together how long it would truly take us to answer that ancient call. Before we can journey to Saturn, we must first understand the nature of distance itself. In our terrestrial lives, distance is simple. A mile is a mile. A road stretches from here to there in a straight, unchanging line. But in space, distance is not a fixed number written on a map. It is a living, breathing relationship between worlds in constant motion, orbiting the sun at different speeds, following paths that spiral and curve through the darkness. Saturn's distance from Earth is not one number, but many, shifting across months and years like the tides of an invisible cosmic ocean. At its closest approach, when Earth and Saturn align on the same side of the Sun, the distance between them is approximately 746 million miles. This is known as opposition, the moment when Saturn appears brightest in our night sky, when the two worlds briefly share the same stretch of solar neighborhood. But the solar system does not pause. Within months, Earth races ahead in its faster orbit, while Saturn, 9 times farther from the Sun, moves with the patient slowness of a giant. The distance between us begins to grow. At its farthest, when Earth and Saturn lie on opposite sides of the Sun, the gulf swells to nearly 1.7 billion miles, more than double the closest distance. This is not merely a number, it is a chasm measured not just in miles, but in years of travel, in fuel consumed, in energy required. To journey to Saturn is to accept that the destination itself is moving, retreating, or approaching, depending on where we stand in our own orbit. The challenge is not simply reaching Saturn, it is reaching Saturn at the right moment, when the geometry of the heavens aligns in our favor. This is where orbital mechanics becomes not just science, but philosophy. Every object in the solar system follows an elliptical path around the Sun, governed by gravity and momentum established billions of years ago. Earth completes one orbit every 365 days. Saturn takes nearly 29.5 years. These differing orbital periods create a rhythm, a celestial dance, where the two planets align favorably only once every 378 days. This window, when the distance is shortest and the energy required is minimal, is called a launch window. Miss it, and we must wait another year for the planets to align again. But even when the launch window opens, we cannot simply point a rocket towards Saturn and fire the engines. Space travel does not work like driving across a highway. The spacecraft must account for the motion of both Earth and Saturn, the gravitational influence of the Sun, and the immense velocities involved. Earth itself is hurtling through space at approximately 67,000 miles per hour as it orbits the Sun. Saturn moves at about 21,000 miles per hour. To reach Saturn, the spacecraft must not aim for where Saturn is, but where Saturn will be months or years into the future. Imagine trying to throw a ball to a friend who is running in a wide circle around you, while you yourself are also running in a smaller, faster circle. You would not throw the ball directly at your friend. You would throw it ahead, anticipating where they will be when the ball arrives. Now multiply the complexity by millions of miles, add the gravitational wells of multiple planets, and account for velocities measured in thousands of miles per hour. This is the reality of interplanetary navigation. Every trajectory is a prediction, a carefully calculated arc through space-time that must account for forces and motions on a scale that defies human intuition. The energy requirements for such a journey are staggering. To escape Earth's gravity and reach the necessary velocity to travel to Saturn demands immense propulsion. Chemical rockets, the workhorses of space exploration, must burn enormous quantities of fuel just to break free from our planet's gravitational embrace. But carrying more fuel adds more weight, which requires even more fuel to lift. This tyranny of the rocket equation places fundamental limits on what is possible with conventional propulsion. A direct route to Saturn, one that simply accelerates continuously toward the planet, would require so much fuel that the spacecraft would become impossibly heavy, too massive to launch with current technology. This is why direct routes are rarely, if ever, used for missions to the outer solar system. Instead, spacecraft follow curving, elegant paths that minimize energy expenditure by working with gravity rather than against it. They loop through the inner solar system, sometimes passing Venus or Earth multiple times, each flyby adding velocity through gravity assists. They spiral outward gradually, trading time for efficiency, months or years for the conservation of precious fuel. The shortest path is not the fastest, and the straightest line is often impossible. Distance in space is also deceptive because it cannot be measured by a ruler stretched through the void. When we say Saturn is 746 million miles away, we are speaking of a snapshot, a single moment frozen in time. But by the time a spacecraft reaches that point in space, Saturn has moved. The actual distance traveled is determined not by the gap between 2 points, but by the trajectory the spacecraft must follow to intercept a moving target. A mission to Saturn might cover well over 1 billion miles, even during a favorable opposition, as the spacecraft arcs outward through the solar system, spiraling along a path dictated by orbital mechanics and the physics of celestial motion. Timing, then, becomes everything. Launch too early or too late, and the spacecraft misses the optimal alignment. The journey becomes longer, more fuel-intensive, perhaps even impossible with the available technology. Mission planners calculate these windows years in advance, accounting for the positions of Earth, Saturn, and any intermediate planets used for gravity assists. The window itself is narrow, sometimes lasting only a few weeks. Within that window, there may be only a handful of days when conditions are ideal. Space exploration is not just about building machines capable of reaching distant worlds. It is about synchronizing human ambition with the ancient rhythms of planetary motion. And yet, even with perfect timing, perfect alignment, and optimal trajectories, the journey remains long. Saturn orbits in a realm where sunlight is 100 times dimmer than on Earth, where the warmth of our star is a distant memory. To reach this world is to travel not just through space, but through layers of cosmic isolation. Every million miles places us farther from the familiar, deeper into a region where silence is absolute, and the void stretches in all directions without end. Understanding Saturn's distance, then, requires more than numbers. It requires an appreciation for motion, for time, for the hidden architecture of the solar system itself. Saturn is not simply far away. It is far away in a specific manner, at a specific time, within a system that never stops moving. The challenge is not overcoming distance alone, but understanding that distance, in space, is always relative, always changing, and always intertwined with the greater dance of worlds around the Sun. This is the foundation upon which every mission to Saturn is built. Not just the engineering, not just the technology, but the recognition that we are not launching into empty space. We are launching into a living system, one that breathes with orbital periods and gravitational currents, where every journey is a negotiation with the cosmos itself. Before we dream of breakthrough propulsion and exotic technologies, we must first understand the reality of reaching Saturn with the tools we already possess. Chemical rockets, the workhorses of space exploration, have carried humanity's ambassadors to every corner of the solar system. Yet when it comes to Saturn, these conventional engines reveal both their remarkable capability and their profound limitations. The journey is measured not just in distance, but in patience, precision, and the unforgiving mathematics of fuel and velocity. When NASA's Cassini spacecraft launched from Cape Canaveral in October 1997, it embarked on what would become one of the most successful missions in the history of planetary exploration. Yet Cassini did not arrive at Saturn until July 2004, nearly 7 years after leaving Earth. 7 years. To put that in perspective, a child born the day Cassini launched would have been starting second grade by the time the spacecraft entered Saturn's orbit. This is the reality of conventional space travel to the outer solar system. It is a journey that demands not just technological excellence, but temporal commitment on a scale that challenges human patience itself. But here is where the story becomes even more fascinating. Saturn, at its closest approach to Earth, is approximately 746 million miles away. Yet Cassini travelled not 746 million miles, but 2.2 billion miles to reach its destination. The spacecraft's path was not a straight line through space, but an elaborate cosmic choreography, looping through the inner solar system, swinging past Venus twice, then Earth, and finally Jupiter, before gathering enough velocity to reach Saturn. This serpentine route was not inefficiency. It was necessity, dictated by the brutal mathematics of chemical propulsion. Chemical rockets operate on a principle that has remained fundamentally unchanged since their invention. They burn fuel to create thrust. The faster you want to go, the more fuel you must carry. But fuel has mass, and carrying more fuel requires more energy to accelerate that mass, which in turn requires even more fuel. This is the tyranny of the rocket equation, a mathematical relationship discovered by Konstantin Tsiolkovsky over a century ago that continues to govern every spacecraft we launch today. To understand this constraint, imagine trying to drive across a continent, but every gallon of fuel in your tank makes your vehicle heavier, requiring more fuel to move it, which makes it heavier still. Eventually, you reach a point where you would need to carry so much fuel that the vehicle cannot lift its own weight. Chemical rockets face this same predicament, amplified by the vast distances of space and the absence of gas stations between planets. Cassini, fully fueled and equipped, weighed nearly 6 tons at launch. Of that mass, more than half was propellant. Even with this enormous fuel load, the spacecraft could not generate enough velocity to reach Saturn directly. Instead, mission planners designed a trajectory that borrowed speed from the planets themselves, using gravity assist to multiply the spacecraft's velocity without burning a single drop of additional fuel. This ingenious solution transformed what would have been an impossible direct journey into a feasible, albeit lengthy, mission. The Voyager missions, launched in 1977, offer a contrasting approach. Voyager 1 reached Saturn in just over 3 years, significantly faster than Cassini's 7-year journey. Voyager 2 arrived in 4 years. How did these spacecraft, launched decades earlier with less advanced technology, make the journey more quickly? The answer lies in their mission design. The Voyagers were not built to stop. They were cosmic messengers designed to fly past Saturn at tremendous speed, capturing data during a brief encounter before continuing into the outer reaches of the solar system and beyond. Cassini, by contrast, was built to stay. To enter orbit around Saturn required the spacecraft to slow down dramatically as it approached, fighting against its own velocity to allow Saturn's gravity to capture it. This deceleration demanded additional fuel, adding mass that had to be accelerated during the initial launch and throughout the gravity assist maneuvers. The trade-off was clear: speed for science. Voyager's rapid flyby offered glimpses. Cassini's patient orbit offered revelation, spending 13 years studying Saturn's rings, moons, and atmosphere in exquisite detail. This brings us to a sobering reality check. With current chemical rocket technology, reaching Saturn requires a minimum of 6 to 7 years, even with optimal launch windows and efficient gravity assist trajectories. There is no shortcut. No amount of clever engineering or advanced fuel chemistry can fundamentally change this timeline without requiring fuel loads so massive they become impractical or impossible to launch from Earth's surface. Consider the New Horizons mission to Pluto, which launched as the fastest spacecraft ever sent from Earth, accelerating to speeds of over 36,000 miles per hour. Even at this remarkable velocity, reaching Saturn would have taken approximately 6 years if that had been its destination. Speed alone, when powered by chemical combustion, can only compress the timeline so much before the physics of propellant mass become insurmountable. The cost implications of these timelines are profound. A 7-year transit means 7 years of mission operations, 7 years of tracking and communication, 7 years of maintaining ground support teams, and 7 years during which the spacecraft must function flawlessly in the harsh environment of space. Solar panels degrade over time. Electronic components suffer radiation damage. Mechanical systems experience wear. Every additional year of transit is another year of risk, another year of budget allocation, another year during which scientific instruments must remain operational and calibrated. Moreover, the payload capacity of chemical rockets limits what can be sent to Saturn. Cassini carried approximately 360 kilograms of scientific instruments, a remarkable achievement, yet still constrained by the fundamental need to carry enough fuel for the journey and orbital insertion. Every kilogram of additional instruments requires additional fuel to accelerate it, which requires more fuel to accelerate that fuel, spiraling back into the rocket equation's unforgiving logic. These are not failures of engineering or imagination. They are simply the boundaries of chemistry and physics as we understand them today. Chemical rockets have achieved extraordinary feats, sending humans to the moon and robotic explorers to every planet in our solar system. They represent a mature, reliable technology refined over decades of innovation. Yet, they also represent a plateau, a limit beyond which conventional propulsion cannot significantly improve the timeline for reaching distant worlds like Saturn. As we drift through the darkness between Jupiter and Saturn, contemplating these constraints, we begin to appreciate why reaching the ringed planet is not merely a question of building a bigger rocket or loading more fuel. It is a question of fundamentally rethinking how we move through space. Chemical combustion has carried us far, but to journey faster, to transport larger payloads, to one day send humans beyond the asteroid belt, we must look beyond the slow boat of conventional technology toward new methods of propulsion that bend the rules rather than submit to them. The 7 years Cassini spent in transit were not wasted time. They were necessary time, dictated by the realities of physics and the tools at our disposal. And yet, as we continue our journey toward Saturn's glittering rings, we cannot help but wonder, what if there were another way? No spacecraft reaches Saturn by traveling in a straight line. The universe does not grant us such simplicity. Instead, we must learn to dance with gravity itself, choreographing a cosmic ballet that transforms distant planets into partners rather than obstacles. This is the gravity assist, a maneuver so elegant in concept yet so demanding in execution that it has defined nearly every mission to the outer solar system. Here, in the vast emptiness between worlds, we discover that the fastest path is rarely the most direct one. A gravity assist is, at its core, an exchange of momentum. Imagine standing on a moving train and catching a ball thrown from the platform. From your perspective on the train, the ball arrives with ordinary speed, but to someone watching from the platform, that ball now carries not just its own velocity, but yours as well. Gravity assists work on the same principle, except the train is a planet orbiting the sun at tens of thousands of miles per hour, and the ball is our spacecraft, catching a fraction of that colossal momentum as it swings past. The beauty of this maneuver lies in its economy. We gain tremendous speed without burning a single drop of fuel. The planet's gravity pulls the spacecraft inward, accelerating it as it falls toward the massive body. Then, if the trajectory is calculated with exquisite precision, the craft arcs around the planet and is flung outward on a new path, traveling faster than it arrived. The planet itself slows down infinitesimally, losing a tiny fragment of its orbital momentum, but the effect is so microscopic that Jupiter or Venus would need to assist millions of spacecraft before anyone could measure the difference. We are borrowing speed from worlds so massive that they never notice the loan. This is not a modern discovery. The possibility was recognized as early as the 1960s, but it was Voyager 1 and Voyager 2 that transformed gravity assists from theoretical curiosity into practical necessity. These twin spacecraft, launched in 1977, were designed to exploit a rare alignment of the outer planets that occurs only once every 176 years. By carefully threading through the gravitational fields of Jupiter, Saturn, Uranus, and Neptune, the Voyagers accomplished what would have been impossible with chemical rockets alone. A direct flight to Neptune would have required 30 years or more. With gravity assists, Voyager 2 arrived in just 12 years, visiting all 4 giant planets along the way. Each encounter was not just a flyby, but a precisely timed slingshot, hurling the spacecraft deeper into the solar system with speeds that would eventually carry them beyond the sun's influence entirely. For a mission to Saturn, the dance typically begins much closer to home. Venus, despite being an inner planet, often serves as the first partner in this gravitational waltz. A spacecraft leaving Earth can swing by Venus, using its gravity to reshape its trajectory and gain speed. This seems counterintuitive. Why would traveling toward the sun help us reach the outer planets? The answer lies in orbital mechanics. By diving closer to the sun and then using Venus's gravity to redirect, we can achieve trajectories and velocities impossible to reach from Earth directly. The Cassini mission to Saturn performed this exact maneuver, flying past Venus not once, but twice, adjusting its path with each pass. From Venus, the spacecraft often returns to Earth for another assist. Our own planet becomes a stepping stone, its gravity providing an additional boost. This Earth flyby is both practical and poignant. The spacecraft passes by the world that built it, receiving one final push from home before venturing into the deep outer system. Some missions have used Earth multiple times, swinging past like a pendulum gathering momentum with each arc. Then comes Jupiter, the grand maestro of gravity assists. Its immense mass makes it the most powerful slingshot in the solar system. A carefully planned Jupiter flyby can add thousands of miles per hour to a spacecraft's velocity, shaving years off the journey to Saturn. The Cassini mission took nearly 7 years to reach Saturn, but without its Jupiter assist in 2000, the journey would have stretched beyond a decade. New Horizons bound for Pluto gained such tremendous speed from Jupiter that it became the fastest spacecraft ever launched, crossing the solar system in record time. Yet this cosmic pinball game demands patience of a particular kind. Taking the long way often means traveling through the inner solar system first, looping past Venus and Earth before finally heading outward. The total distance covered can be 2 or 3 times greater than a direct path. A spacecraft might travel for years in what appears to be the wrong direction, edging closer to the Sun when its destination lies far beyond Jupiter's orbit. Mission planners must balance trajectory against launch windows, fuel reserves against time, speed against scientific objectives. Sometimes the most efficient path requires waiting years for planets to align properly, delaying the entire mission for a single optimal geometry that may not repeat for decades. The calculations required are staggering. Engineers must predict not just where a planet will be in several years, but where it will be to within meters after the spacecraft has traveled billions of miles. They must account for the gravitational influence of every body in the solar system, the pressure of sunlight on the spacecraft's surfaces, even the tiny thrust produced when the craft vents excess heat. A miscalculation of mere feet per second during a flyby can translate to missing Saturn entirely, sending the spacecraft tumbling uselessly into the void. Cassini's trajectory serves as the masterpiece example of this gravitational choreography. Launched in 1997, it flew past Venus in 1998, returned to Venus again in 1999, swung past Earth in 1999, and finally reached Jupiter in 2000 before arriving at Saturn in 2004. 4 gravity assists, spanning 7 years, each one executed with flawless precision. The alternative would have been a direct flight requiring far more fuel than any rocket could carry, or a journey lasting well over a decade with limited ability to slow down upon arrival. There is risk woven into this elegance. A single malfunction, a software error, a thruster that fires at the wrong moment can doom the entire mission. During flybys, spacecraft often pass through intense radiation belts or navigate perilously close to planetary moons. Cassini passed within 6 million miles of Jupiter, a distance that sounds vast but is razor-thin in cosmic terms, threading through a region where radiation could have fried its electronics in moments. The tension in mission control during these maneuvers is palpable. Years of work, billions of dollars, humanity's reach toward the stars, all compressed into a few hours where nothing can be adjusted, nothing corrected. The spacecraft is alone, executing commands uploaded weeks earlier, flying through a gravitational maelstrom at speeds where even light takes minutes to bring news of success or failure. Yet when the dance succeeds, when the spacecraft emerges from behind a planet with exactly the right velocity and heading, something profound has occurred. We have not conquered gravity, we have conversed with it. We have used the natural architecture of the solar system itself as our engine, turning orbital mechanics into poetry. Every gravity assist is a reminder that space exploration is not about dominating nature through brute force, but about understanding it so deeply that we can move within its currents like leaves on a cosmic wind. As our trajectory carries us past Jupiter and toward the golden realm of Saturn, we travel faster than we left Earth, propelled not by fire, but by the patient orbital dance of worlds we will never touch. The journey is longer, the path more complex, but we arrive not as invaders forcing our way through space, but as students who have learned to read the gravitational language written in planetary motion. This is how we reach Saturn, not by racing in a straight line, but by waltzing through the solar system, borrowing speed from the very worlds we came to explore. If we were to launch a mission to Saturn today, this very moment, what would it look like? Not a dream decades away, but a real spacecraft built with real technology, lifting off from a real launch pad under the glow of cameras and the weight of human aspiration. The answer is both thrilling and humbling, for we possess the capability now to reach Saturn within our lifetimes. Yet the journey remains a testament to patience, precision, and the willingness to embrace the long view of exploration. A modern Saturn mission would be fundamentally different from Cassini, the legendary spacecraft that arrived at Saturn in 2004 after a 7-year journey. Since then, our technology has evolved in subtle but significant ways. Rocket engines burn more efficiently. Spacecraft materials have become lighter and stronger. Solar panels generate more power from less surface area. Computers process information faster while consuming less energy. These incremental advances may not sound revolutionary, but in the mathematics of space travel, small improvements compound across vast distances into something profound. If we launch today using optimal technology, a spacecraft could reach Saturn in approximately 5 to 6 years, possibly even faster if we were willing to accept certain trade-offs in scientific capability. This timeline assumes a trajectory similar to what modern mission planners call a fast transfer, utilizing a direct path with minimal planetary flybys, or perhaps a single gravity assist from Jupiter to gain the necessary velocity without excessive detours. The engineering is not theoretical. It exists on drawing boards, in computer simulations, and in the minds of scientists who have spent careers calculating these cosmic pathways. But timing is everything. Saturn does not wait for us, nor does Earth linger in convenient positions. The planets move in their eternal dance around the Sun, and launch windows, those precious alignments when trajectories are most efficient, open and close with celestial regularity. For Saturn, optimal launch windows occur roughly every 13 months, brief periods lasting only a few weeks when the geometry of the solar system favors our departure. Miss the window, and you must wait another year, or accept a longer, more fuel-intensive route that could add months or even years to the journey. The next truly optimal launch window for a Saturn mission will arrive within the coming years, a moment when Earth and Saturn will align in such a way that our spacecraft can traverse the distance with maximum efficiency. Mission planners monitor these windows decades in advance, building trajectories like architects design cathedrals, knowing that every calculation must account for forces both known and uncertain. Gravity, radiation, orbital mechanics, fuel reserves, instrument calibration. All must harmonize into a single thread of motion, stretching across the solar system. Since Cassini's era, our propulsion systems have matured. Modern chemical rockets deliver greater thrust with improved specific impulse, meaning they extract more momentum from every kilogram of fuel. Spacecraft construction has embraced composite materials and advanced alloys that reduce mass without sacrificing structural integrity. Every kilogram saved is a kilogram that can be accelerated faster, or a kilogram that allows for additional scientific instruments, or simply more fuel to adjust course during the long voyage. In space exploration, mass is not just a number, it is destiny. Communication systems have also advanced remarkably. While Cassini's radio signals took over an hour to travel from Saturn to Earth, creating vast delays in command and response, modern spacecraft utilize more sophisticated antennas and higher data transmission rates. Future missions could employ laser communication systems, capable of sending images and data at speeds unimaginable just 2 decades ago. Yet no technology can overcome the fundamental constraint of distance. Even traveling at the speed of light, signals from Saturn require roughly 70 to 90 minutes to reach Earth, depending on the planet's positions in their orbits. This delay transforms mission control into an exercise in patience and foresight. Controllers on Earth cannot pilot the spacecraft in real time. Every command must be sent hours before it is needed, every maneuver planned with the assumption that conditions will remain stable during the communication gap. The spacecraft must possess a degree of autonomy, capable of making critical decisions on its own if danger arises. In this way, modern missions are not merely vessels we control from afar. They are emissaries, semi-independent explorers carrying our intentions into the void. But could we send humans on such a journey? Could astronauts endure 5 to 6 years in transit, sealed inside a spacecraft hurtling through the darkness toward a ringed giant they can barely see with their naked eyes? The question is as much psychological as it is technical. Physically, we've learned much from long-duration missions aboard the International Space Station. We know how to sustain human life in space for months, even years. We understand the effects of microgravity on bones and muscles, the challenges of radiation exposure, the necessity of recycling air and water with near-perfect efficiency. Yet Saturn is not the International Space Station. There would be no resupply missions, no emergency return capsules, no abort-to-Earth option once the spacecraft reaches a certain distance. Astronauts bound for Saturn would be committed to the journey in a way that no human has ever been committed before. They would watch Earth shrink to a pale blue dot, then vanish entirely into the sun's glare. They would drift through the asteroid belt, loop past Jupiter, and continue onward into a realm where the sun itself becomes little more than a bright star among stars. The human factor introduces complexities that machines do not face. Psychological isolation, the strain of confinement, the existential weight of knowing that every passing day places you farther from home. These are not engineering problems to be solved with better materials or smarter computers. They are human problems, requiring human solutions. Space agencies have begun studying these challenges in earnest, designing habitats with artificial gravity, developing virtual reality environments to combat monotony, training astronauts in techniques to maintain mental health across years of isolation. A crewed mission to Saturn, if launched today with current technology, would be at the very edge of what is possible. Not impossible, but extraordinarily difficult, demanding levels of planning, redundancy, and courage that stretch the limits of human endeavor. It would require international cooperation on an unprecedented scale, pooling resources and knowledge from nations across Earth. And it would require a willingness to accept risk, for space exploration has never been, and will never be, without danger. So, if we left today, what would we choose? A robotic mission, fast and efficient, capable of reaching Saturn in 5 to 6 years, with instruments that can see, measure, and analyze in ways human senses cannot. Or a crewed mission, slower perhaps, heavier certainly, but carrying within it the spark of human curiosity, the ability to adapt and respond to the unexpected in real time. Both paths are open to us, both are valid, and both represent the enduring question at the heart of all exploration. Are we seeking knowledge alone, or are we seeking to expand the frontier of human presence itself? The choice we make will define not just how long it takes to reach Saturn, but why we go at all. But what if the journey need not take 7 years? What if we could reach Saturn not through patience alone, but through propulsion systems that defy the limitations of conventional rockets? We stand now at the threshold of technologies that could transform the solar system from an ocean of years into a realm of mere months. The dream is not distant. It glimmers on the horizon, powered not by chemical fire, but by the patient acceleration of ions, the controlled fury of nuclear reactions, and plasma streams that flow like rivers of light. Ion propulsion represents one of humanity's most elegant solutions to the challenge of deep space travel. Unlike traditional rockets that burn fuel in violent bursts, ion drives operate on a principle of sustained whisper. They accelerate ions, electrically charged atoms, through electromagnetic fields, expelling them at extraordinary speeds to generate thrust. The force produced is gentle, barely enough to lift a sheet of paper on Earth. Yet in the vacuum of space, this continuous acceleration compounds over time, eventually propelling spacecraft to velocities chemical rockets cannot match. The beauty of ion propulsion lies not in its power, but in its persistence. Imagine pushing a child on a swing, not with a single mighty shove, but with countless gentle nudges, each building upon the last, until the arc becomes greater than any single push could achieve. This is how ion drives work. They do not roar, they hum. Over weeks and months, that hum becomes a song of accumulating speed, transforming spacecraft into vessels capable of reaching Saturn in 3 to 4 years instead of 7, perhaps even less with refinements yet to come. NASA's Dawn mission demonstrated this capability with remarkable success. Launched in 2007, Dawn used ion propulsion to visit both Vesta and Ceres in the asteroid belt, becoming the first spacecraft to orbit 2 extraterrestrial bodies. Its ion engine operated for over 5.9 years of cumulative thrust time, far longer than any chemical rocket could sustain. The spacecraft changed its velocity by over 25,000 miles per hour throughout its mission, a feat that would have required impossibly large amounts of conventional fuel. Dawn proved that ion drives are not theoretical curiosities. They are practical, reliable, and ready for missions to the outer planets. Current ion propulsion systems use xenon gas as propellant, ionizing it and accelerating it through electric grids powered by solar panels or nuclear reactors. The efficiency is staggering. Ion drives can be 10 times more fuel efficient than chemical rockets, meaning spacecraft can carry less propellant and more scientific instruments, or achieve greater speeds with the same mass. For a mission to Saturn, this efficiency translates directly into time saved. Each kilogram of propellant goes farther, each watt of power pushes harder, and the accumulating velocity shortens the journey by years. But ion drives are merely the beginning. Beyond them lies nuclear propulsion, a concept that has haunted and inspired engineers for decades. Nuclear thermal propulsion works by heating hydrogen propellant with a nuclear reactor, then expelling it through a nozzle at temperatures exceeding 4,500 degrees Fahrenheit. The thrust produced is far greater than ion drives, yet still far more efficient than chemical rockets. Estimates suggest that nuclear thermal rockets could cut the journey to Saturn to as little as 3 years, perhaps less, with aggressive trajectories and gravity assists. The technology is mature, tested extensively during the 1960s and 70s in programs like NERVA, which successfully demonstrated nuclear rocket engines that could operate reliably for extended periods. Nuclear electric propulsion takes a different approach. Instead of heating propellant directly, a nuclear reactor generates electricity, which then powers ion drives or other electric thrusters. This combination offers the best of both worlds, the sustained efficiency of ion propulsion with the abundant power only nuclear reactors can provide far from the sun. In the outer solar system, where sunlight dims to a faint whisper, solar panels become inadequate. Nuclear reactors shine brightest in the darkness, providing continuous power for months or years, enabling spacecraft to accelerate relentlessly toward their distant targets. NASA and other space agencies are actively developing these systems. The agency's Kilopower project has successfully tested small nuclear reactors designed for space use, while nuclear thermal propulsion has been prioritized for missions to Mars and beyond. The technology is not science fiction awaiting invention. It is engineering awaiting implementation, a matter of refining designs, conducting tests, and overcoming the political and regulatory challenges that surround anything nuclear. Herein lies the paradox. The greatest obstacles to nuclear propulsion are not technical, but societal. Launching nuclear reactors into space raises legitimate concerns about safety. What happens if a rocket carrying a reactor fails during launch? How do we ensure that radioactive materials never threaten Earth's environment? These questions demand careful answers, robust safety systems, and transparent dialogue between engineers, regulators, and the public. Yet the risks, while real, are manageable. Reactors can be designed to remain inert until safely in space, activated only after reaching orbit. Fuel can be loaded in configurations that make accidental criticality impossible. Containment systems can protect payloads during any conceivable failure scenario. The conversation around nuclear space propulsion is not about whether it can be done safely, it can, but whether we collectively choose to embrace it. Many nations have successfully launched nuclear-powered spacecraft before. The Soviet Union's Rorsat satellites, NASA's radioisotope, thermoelectric generators powering missions like Voyager and Curiosity, all demonstrate that nuclear power in space is a proven reality. Scaling these systems to propulsion is the next logical step, one that could open the outer solar system to exploration timelines measured in years instead of decades. Beyond nuclear systems lies an even more ambitious frontier: plasma propulsion, exemplified by engines like VASIM-R, the Variable Specific Impulse Magnetoplasma rocket. Developed by former astronaut Franklin Chang Diaz, VASIM-R uses radio waves to heat gas into plasma, then channels that plasma through magnetic fields to generate thrust. The engine can adjust its performance dynamically, operating in high thrust mode for rapid acceleration or high efficiency mode for extended cruising. In theory, a VASIM-R-powered spacecraft could reach Saturn in as little as 2 to 3 years, cutting travel time nearly in half compared to conventional missions. VASIM-R and similar plasma engines remain in development, their full potential yet unrealized. Ground tests have demonstrated the technology's viability, but a full-scale space demonstration has yet to occur. The challenge is not whether plasma propulsion works, but whether we can build systems powerful enough, reliable enough, and efficient enough to justify their complexity for deep space missions. Every advancement brings us closer. Every test refines our understanding. The engines hum in laboratories today, preparing for the day they will hum in the void, pushing humanity towards Saturn and beyond. These technologies, ion drives, nuclear thermal and electric propulsion, plasma rockets, are not fantasies borrowed from science fiction. They are the fruits of decades of research, testing, and incremental improvement. The physics is well understood. The engineering is mature. What remains is commitment, the collective decision to invest resources, navigate political landscapes, and accept the risks inherent in pioneering new frontiers. The journey to Saturn need not take 7 years. With the technologies emerging today, it could take 4 years, 3 years, perhaps even less. As we contemplate these nuclear dreams and electric whispers, we must remember that speed alone is not the goal. These propulsion systems do not merely shorten travel time, they expand possibility. They enable missions with larger payloads, more instruments, greater redundancy. They allow spacecraft to maneuver in orbit, hopping between moons, adjusting trajectories, extending missions far beyond their original plans. They transform the outer solar system from a destination requiring decades of planning and years of waiting into a realm within practical reach. The door to Saturn is opening, not with the roar of chemical fire, but with the patient acceleration of ions and the control power of atoms split for propulsion. These are the technologies that will carry us forward, that will turn the dream of regular exploration into routine reality. The universe does not yield easily to human ambition, but it does yield to ingenuity, persistence, and the quiet confidence that what seems impossible today becomes merely difficult tomorrow, and routine the day after. Beyond the proven methods of chemical rockets and ion drives, there exists a realm of propulsion concepts that blur the line between engineering and imagination. These are the wild cards, the breakthrough technologies that could transform a 7-year journey to Saturn into a matter of months, or perhaps even weeks. Some exist only in theoretical physics papers. Others are being tested in laboratories right now. All share a common thread. They challenge our assumptions about what is possible when journeying through the solar system. Consider for a moment the concept of a solar sail, a spacecraft propelled not by burning fuel, but by capturing the gentle pressure of photons streaming from the sun. Light, despite having no mass, carries momentum. When photons reflect off a mirrored surface, they impart a tiny push, imperceptible on Earth, but profound in the vacuum of space where no friction exists to slow the craft. A solar sail is elegant in its simplicity. Unfurl a vast reflective sheet, sometimes measuring miles across, and let starlight itself become your engine. The Japan Aerospace Exploration Agency has already demonstrated this technology with Icaros, a spacecraft that successfully sailed through the inner solar system powered only by sunlight. For a mission to Saturn, a solar sail would accelerate continuously, day after day, slowly building velocity without consuming propellant. The journey would be silent, graceful, and extraordinarily patient. Unlike conventional rockets that burn their fuel in minutes and coast for years, a solar sail never stops accelerating. The farther from the sun it travels, the weaker the photon pressure becomes, yet the momentum already gained carries it forward, compounding with each passing day. Could we ride photons all the way to Saturn? The mathematics suggests it is possible, though not yet practical for crewed missions. A solar sail large enough to carry substantial payload would need to be gossamer thin, precisely oriented, and resilient enough to withstand micrometeorite impacts across years of flight. The time savings compared to conventional propulsion would be modest, perhaps shaving a year or two from the journey. But the concept points towards something profound. Propulsion without propellant, movement without fuel, travel sustained by the fundamental architecture of light itself. Yet solar sails are only the beginning. Some researchers envision augmenting them with powerful lasers beamed from Earth or orbital stations, concentrating photon pressure to accelerate the sail far beyond what sunlight alone could achieve. This is laser propulsion, a concept where the energy source remains stationary while the spacecraft rides a beam of focused light across the void. The Breakthrough Starshot Initiative has proposed this very approach for reaching nearby stars, using gigawatt-class laser arrays to propel tiny spacecraft to a fraction of light speed. Scaled appropriately, similar technology could dramatically reduce transit time to Saturn. Imagine a spacecraft unfurling its sail in Earth orbit, then suddenly bathed in the concentrated power of ground-based lasers. The acceleration would be intense, pushing the craft to velocities unattainable through any onboard propulsion system. Within weeks, it could reach speeds that would bring Saturn within range in months rather than years. The challenge, of course, lies in maintaining laser focus across millions of miles, compensating for the spacecraft's motion, and ensuring the sail can withstand the thermal stress of such intense energy. These are not insurmountable obstacles, but they are formidable, requiring precision engineering on a scale humanity has never attempted. Moving beyond light, we enter the realm of fusion propulsion, where the very power that lights the stars becomes the engine of our spacecraft. Nuclear fusion, the process of merging light atomic nuclei to release tremendous energy, has tantalized scientists for decades. On Earth, achieving controlled fusion remains an elusive goal, always seeming just beyond our grasp. In space, however, the requirements are different. A fusion drive does not need to generate electricity for a power grid. It needs only to superheat propellant and expel it at extraordinary velocities, creating thrust far exceeding anything chemical rockets can achieve. Theoretical fusion engines could accelerate a spacecraft to Saturn in a matter of months, continuously burning fuel throughout the journey, first accelerating to the midpoint, then flipping around and decelerating for arrival. The exhaust velocity of fusion plasma would be measured in percentages of light speed, making even ion drives seem sluggish by comparison. Time itself would compress. What once took years would take seasons. Crew members might leave Earth in spring and arrive at Saturn before winter's end. The obstacles to fusion propulsion are primarily technological, not theoretical. Containing plasma at temperatures hotter than the core of the Sun, sustaining the fusion reaction in the vacuum of space, managing radiation, and miniaturizing reactors to fit aboard spacecraft are all challenges requiring breakthroughs in materials, science, magnetic confinement, and reactor design. Some experimental designs propose using pulses of laser-ignited fusion pellets, each micro-explosion creating thrust in rapid succession. Others envision magnetic bottles holding continuous fusion reactions. All share the promise of transforming interplanetary travel from an endurance test into a swift transit. And then, at the edge of what current physics allows, there is antimatter. When matter and antimatter meet, they annihilate completely, converting 100% of their mass directly into energy according to Einstein's most famous equation. No other reaction in the universe is more efficient. A single gram of antimatter reacting with a gram of matter would release the energy equivalent of several nuclear bombs. Channeled properly, this energy could propel a spacecraft to Saturn in weeks. Antimatter propulsion is not science fiction. It is established physics applied to extraordinary engineering problems. NASA and other agencies have studied antimatter engines for decades. The challenges are staggering. Producing antimatter requires particle accelerators and consumes enormous amounts of energy. Currently, humanity produces only nanograms of antimatter per year, at costs measured in trillions of dollars per gram. Storing antimatter without letting it touch ordinary matter and annihilate prematurely requires magnetic traps of unprecedented sophistication. Yet, if these obstacles could be overcome, if antimatter could be produced and stored efficiently, it would revolutionize not just travel to Saturn, but our entire relationship with space. An antimatter-powered craft might reach Saturn in less than a month, its crew experiencing what previous generations would have considered impossible. A journey to the outer solar system completed within a single season. The rings of Saturn would no longer represent years of anticipation, but merely weeks of travel, bringing the outer planets within reach of human careers, human lifespans, human patience. These wild cards, solar sails and laser propulsion, fusion drives and antimatter engines, represent more than technological advancement. They represent philosophical shifts in how we approach the cosmos. They suggest that distance, which once seemed an absolute barrier, might be merely a temporary limitation. That the years required to reach Saturn are not immutable facts of physics, but challenges awaiting the right breakthrough. Not all of these concepts will succeed. Some may remain theoretical indefinitely, beautiful ideas that never quite translate into working hardware. Others might surprise us, leaping from laboratory prototypes to operational spacecraft within decades. The history of spaceflight teaches us that today's wild speculation often becomes tomorrow's routine operation. As we contemplate these possibilities, we are reminded that exploration is not just about reaching destinations. It is about expanding what we believe is reachable. Every breakthrough propulsion concept, however speculative, pushes the boundary of the possible outward. They invite us to imagine a future where Saturn is not a distant jewel requiring years of patience to visit, but a neighboring world we can reach within the span of a single human journey, where the question is no longer whether we can go, but simply when we choose to depart. The journey to Saturn is often described in numbers: millions of miles, years of travel, velocities that defy intuition. But hidden inside those grand statistics is something far more fragile and far more complex: us, human beings, soft, biological, emotional creatures trying to cross a realm built for vacuum, radiation, and silence. On paper, a 5 to 7 year trip to Saturn is a triumph of engineering and orbital mechanics. Inside the spacecraft, it is something else entirely. It is a challenge to the human body, the human mind, and the entire idea of what it means to be away from home. Imagine the clock of your life stretching out across deep space. Birthdays, seasons, entire phases of your personal story unfolding, while the view out the window barely changes. Stars remain fixed. The sun slowly dwindles from a familiar disk into a distant, brilliant point. Earth becomes a pale star that grows dimmer with every passing month, until it is no longer a world you left, but a memory you carry. For the crew, the vastness of the journey is not simply distance, it is duration. In low Earth orbit, astronauts can look down and see continents drift beneath them in minutes. On the way to Saturn, there is no blue planet filling the window, no rapid sunrise every 90 minutes to mark time. Days blend into weeks. Weeks flow into months. The rhythm of time is no longer set by Earth's rotation, but by scheduled tasks, routine exercises, and the slow, steady thrum of life support systems working tirelessly in the background. Psychologically, this is a frontier we have only begun to glimpse. On the International Space Station, crews stay for 6 months, sometimes a year. They are a phone call away from family, a video link away from real-time conversation. If something goes wrong, a spacecraft can return them to Earth in hours. Even a mission to Mars, as ambitious as it is, still fits within the scale of human patience. Roughly 2 to 3 years round trip, with light time delays that stretch communications to minutes, not hours. Saturn is different. By the time a human crew reach the orbit of the ringed world, radio signals from Earth would take more than an hour to arrive, and another hour to return. A simple question could spend an entire afternoon traveling through the void. The comforting illusion that home is just a call away would disappear. In its place would be something far more unsettling. The realization that in every moment that matters, the crew is truly on its own. Isolation at that scale is not just about physical distance. It is about emotional distance. Celebrations and losses on Earth would reach the crew as delayed echoes. A child's first steps, a loved one's illness, a world event. Everything arrives late. The crew lives in a different time, out of sync with the planet that raised them. Psychologists studying analog missions in remote habitats, underwater stations, and Antarctica have seen what happens when small groups live together in tight quarters for long periods. Friction grows over trivial habits. Tiny misunderstandings can feel enormous. Even with well-trained professionals, morale can dip, motivation can waver, and the simple act of waking up to the exact same walls every day becomes its own quiet test of endurance. Now stretch that from months to years. Beyond the inner planets, another invisible challenge begins to build: radiation. Closer to Earth, our planet's magnetic field serves as a shield, deflecting charged particles from the sun and cosmic rays from distant supernova. In deep space, far from that protective bubble, radiation becomes a constant, subtle storm. A 5 to 7 year voyage to Saturn would expose crews to far more radiation than any astronauts have ever experienced. Solar flares could unleash bursts of energetic particles capable of damaging cells, DNA, and electronics alike. Galactic cosmic rays, high-energy particles traveling near the speed of light, would arrive from all directions, unrelenting, passing through metal and tissue with ease. We can add shielding, layers of water, plastic, or specialized materials that absorb or deflect radiation. We can tuck sleeping quarters deep within the spacecraft's mass. We can design storm shelters, small, heavily shielded rooms where the crew can retreat during solar events. But every kilogram of protection adds weight, and every kilogram of weight demands more fuel. Spacecraft design becomes a negotiation between safety and feasibility, between what we wish we could bring and what we can realistically carry. And radiation is only one piece of the biological puzzle. In microgravity, the human body quietly begins to forget Earth. Bones no longer bear weight, and so they start to lose density. Muscles no longer push against the pull of gravity, and so they begin to weaken. Fluids shift upward, pressing on the eyes and changing vision. The heart, no longer pumping against gravity, can slowly decondition. On the space station, astronauts combat this with hours of exercise every single day, treadmills with restraints, resistance machines that simulate weightlifting, cycling devices bolted to the floor. Even then, some bone and muscle loss is inevitable. Returning crew members need time to readapt, to relearn what it means to stand, balance, and walk in a world where down is once again a direction. Now imagine not 6 months, but years in this environment, with no guarantee that at the other end of the journey, there will be a safe gravity to return to. Saturn itself has no solid surface to land on. Any human expedition would likely orbit the planet or visit its moons, like Titan or Enceladus. That means more time in low gravity or microgravity, more time for the body to drift away from the blueprint it evolved under. Medical emergencies become problems of distance as well as biology. On Earth, a broken bone, an infection, an unexpected illness can call upon an entire global network of hospitals, experts, and supplies. On a spacecraft halfway to Saturn, medical care is what you brought with you and what you know already. There are no resupplies, no quick evacuations, no emergency room waiting quietly just beyond the atmosphere. Every medication must be pre-selected. Every procedure must be something the crew can realistically perform in cramped microgravity conditions, possibly with limited tools. Telemedicine, a doctor on Earth guiding a procedure, now contends with hour-long signal delays. Diagnose incorrectly and precious supplies could be wasted. Intervene too late, and there is nowhere else to turn. This is what makes a Saturn mission exponentially harder than a mission to Mars, even if the spacecraft and propulsion systems were somehow similar. The distance, the duration, the communication lag, the sheer impossibility of rapid rescue, each one compounds the others. Mars is another planet. Saturn is another regime. And yet, human imagination is already reaching for solutions. One concept is as old as the rotating space stations of science fiction: artificial gravity. If we cannot bring Earth's pull with us, perhaps we can simulate it. A rotating habitat, spinning like a slow wheel in space, could use centrifugal force to press the crew gently against its outer wall, mimicking the sensation of down. By carefully adjusting the rotation rate and radius, Engineers could aim for Mars-like gravity, lunar gravity, or even full Earth gravity. Such a structure would be complex, but the promise is immense. Bones and muscles could stay stronger. Fluids could settle more naturally. The human body might no longer feel like it is quietly unraveling over the years. Daily exercise would still matter, but it might no longer be a desperate race against time. Another idea looks not to motion, but to sleep. Some researchers have wondered, could we place astronauts into a state of torpor, a kind of controlled hibernation for long-duration journeys? In nature, animals lower their metabolism, conserve energy, and sleep through harsh seasons. If humans could safely enter a similar state, the psychological burden of isolation might be eased. Food and water consumption could drop. The endless repetition of days could become a single, continuous blur. So far, human hibernation remains theoretical. Experiments on Earth explore how cooling the body or adjusting certain chemicals might protect tissues and organs. Intensive care units sometimes induce controlled hypothermia to protect the brain after injury. These are clues, not blueprints. To place a crew in torpor for months, then reliably wake them, healthy, alert, and intact, would require breakthroughs in medicine that we have not yet achieved. Beyond rotating habitats and hibernation lies an even more radical vision: generation ships. Instead of sending one crew to Saturn and back, imagine a vessel where the journey itself is a civilization. Children are born on board. They grow up never having seen Earth's sky, never having run across its fields. For them, the ship is the world. Saturn would not be a destination, but an inheritance passed down through generations. For a mission within our solar system, generation ships are not a practical necessity. The distances, while immense, are not so great as to demand multiple lifetimes. But the idea reveals something important. When we push far enough, the boundaries between mission and society begin to blur. A voyage to Saturn, with its years of isolation, its reliance on closed, self-sustaining environments, begins to feel less like a trip and more like the seed of a new kind of human community, one that must learn to live inside a finite ecosystem with no outside world to lean on. Closed-loop life support is at the heart of this transition. To survive for years without constant resupply, a Saturn ship must become a miniature Earth. Water is recycled and purified endlessly. Air is scrubbed of carbon dioxide and replenished with oxygen. Waste is not discarded. It is transformed, turned back into nutrients, materials, resources. We already practice early versions of this on the space station. Urine is recycled into drinking water. Carbon dioxide is removed from the air using chemical filters. But the loop is not yet truly closed. Regular cargo flights from Earth bring fresh food, spare parts, and new equipment. On a Saturn journey, resupply becomes impossible. Every leak, every malfunction, every tiny inefficiency would be a problem that accumulates over years. Designing such a life support system is an engineering challenge. Living within it is a human one. The crew would be constantly aware that everything they breathe, drink, and eat is part of a fragile cycle. There is no away to throw things to. Every object, every drop of water, every molecule of air is part of a finite inventory that must last until the mission's end. In this way, a Saturn mission becomes a mirror held up to our own planet. Just as the crew must carefully manage their ship's closed ecosystem, humanity must steward Earth's biosphere, our one great habitat in the vacuum of space. When we ask, how long would it really take us to reach Saturn? We are also asking, how long can we remain ourselves in the vastness of the journey? Years in transit mean more than propulsion and fuel. They mean learning how to carry our bodies, our minds, our relationships, and our entire way of living across a gulf where rescue cannot follow. The distance to Saturn challenges physics. The time to Saturn challenges humanity. Out here between Jupiter and Saturn, distance tempts us. The darkness is vast, the years are long, and somewhere in the back of the human mind, a simple question whispers, why not just go faster? In everyday life, speed is almost always the solution. Faster cars, faster internet, faster flights. But in space, speed comes with a cost so steep it reshapes the mission itself. Every extra mile per hour we gain on the journey to Saturn must be paid for. In fuel, in mass, in complexity, and sometimes in the very science we came here to do. Imagine a scale, hanging in the quiet of space. On one side, speed. On the other, everything that makes the mission worthwhile. Cameras, spectrometers, landing probes, fuel for course corrections, even the shielding that keeps those instruments safe. Add more speed, and the other side must become lighter. There is no escape from this balance. It is written into the physics of rocketry. The rockets that lift us off Earth are already titans, burning oceans of propellant in minutes. Yet only a tiny fraction of what leaves the launch pad is the spacecraft itself. Most of it is fuel. And once we are free of Earth's gravity, that fuel suddenly becomes even more precious, because now it has to do not just one job, but two. It has to speed us up and slow us down. This is where the story of Saturn becomes more than just a race against distance. Getting there quickly is only half the journey. The other half is learning how to stop. Cassini, the spacecraft that gave us our most intimate view of Saturn, was not the fastest traveller ever sent to the outer solar system. It did not blaze a straight trail like a bullet fired toward a target. Instead, it took the long way around, swinging past Venus twice, Earth once, and then Jupiter, borrowing speed from each world in a carefully choreographed dance. 7 years from launch to arrival. For some, that might sound painfully slow, but that slowness was deliberate, and it was the key to Cassini's success. When Cassini reached Saturn, it did not merely glance past and flee into the dark. It arrived with a purpose: to stay, to orbit, to circle the planet again and again, threading through the rings, visiting the moons, studying storms that mutate over seasons rather than days. To do that, Cassini had to do something far more difficult than going fast. It had to hit the brakes. At interplanetary speeds, slowing down is not like easing off the gas pedal. There is no friction here to bleed away momentum, no air to push against, no road to grip. To change your speed, you must burn fuel, and to carry that fuel, you must launch it from Earth, fighting against Earth's gravity. This creates a paradox. The faster you want to go, the more fuel you need to both accelerate and then decelerate later. But the more fuel you carry, the heavier the spacecraft becomes. And the heavier it is, the more fuel you need just to move it. This is the tyranny of the rocket equation, an invisible law that sits behind every mission plan. It is why some spacecraft, like Voyager, are built to fly by outer planets at great speed, capturing quick snapshots as they slingshot outward into the void, while others, like Cassini, are slowed, captured, and allowed to linger. A flyby is like running through an art museum at full sprint. You see the shapes, the colours, a a flash of something beautiful. But then it's gone, receding behind you, forever. The fuel bill is lower, the engineering is simpler, the travel time is shorter. But the time you spend at your destination is just a heartbeat. Orbit is different. Orbit is staying until you understand. To make Cassini an orbiter instead of a passerby, engineers sacrificed speed for control. They used gravity assists not merely to go faster, but to shape the trajectory so that when Cassini finally reached Saturn, it would arrive with a speed that its engines could realistically reduce. They threaded the spacecraft through the gap between Saturn and its rings, using the planet's own gravity to bend and tame its path. In that tense, silent hour of Saturn orbit insertion, Cassini turned its main engine toward its direction of travel and fired, pouring precious fuel into a single, carefully measured burn. That burn was not about racing ahead. It was about staying. And staying meant Cassini could do something flyby missions never could. It could trade seconds of high-speed rush for years of patient watching. It could map storms as they evolved, witness ring structures changing over time, discover geysers of water and organic molecules erupting from Enceladus, and watch Titan's orange haze conceal and reveal lakes of liquid methane. It could return, orbit after orbit, to ask Saturn new questions. Every pound of fuel that made that possible took the place of something else that might have flown. A larger camera, an extra probe, more shielding. Or, conversely, every additional instrument added to the payload meant less room for propellant. Mass is the currency of space exploration, and nothing on a spacecraft is free. When mission designers sit around tables on Earth, they don't just ask, how fast can we get there? They ask, what are we willing to leave behind to make that happen? Do we choose a fast flyby, trading detail for breadth, visiting multiple worlds in a single sweep? Or do we choose the long, slower path, building a mission that can orbit, land, sample, and listen for faint signals over many years? This is not simply a technical question. It is an economic one. Every mission is a negotiation with reality, financial as much as physical. Launch vehicles cost billions. Spacecraft development spans decades. Space agencies operate within budgets set by governments and taxpayers. Faster missions often demand more powerful rockets, more complex propulsion systems, and more stringent engineering tolerances. All of these raise the cost. Sometimes the budget says, you get one shot, one quick pass, make it count. That was Voyager. Moving fast, but carrying a small symphony of instruments, it offered a grand tour at the price of permanence. It would not stay anywhere, but it would see everything. Jupiter, Saturn, Uranus, Neptune, before vanishing into interstellar night. Other times, the decision is different. Saturn, with its rings and moons and mysteries, was judged worthy of a slower, more deliberate approach. Instead of speed, Cassini brought endurance. Instead of a single encounter, it brought an era of observation. In the end, the question of how long would it actually take to reach Saturn hides another deeper question. What do we want to do once we get there? If we only wish to prove we can arrive quickly, we can. We have the technology to fling a small, hardened probe across the gulf in just a few years, racing past Saturn in a blur of data and static. But if we want to orbit, to descend through Titan's clouds, to count the ripples in Saturn's rings, and listen to the whisper of charged particles in its magnetic field, then we must move more slowly. We must carry more fuel, more instruments, more patience. Speed is thrilling. But in the quiet dark of the outer solar system, science often belongs to those who linger. As our imagined spacecraft continues on its path towards Saturn, it carries not just engines and experiments, but a decision already made back on Earth. A choice to arrive not as a tourist sprinting through the gallery of worlds, but as a long-term guest, willing to trade haste for understanding. In that trade-off, the true journey begins. Saturn glows in the darkness like a lantern at the edge of a forgotten road, but for now, it remains a place we visit only with silent machines. As our thoughts drift across the rings, another question forms in the quiet. When will we stop sending only metal and circuits and send ourselves? To answer that, we have to look not just at Saturn, but at the story humanity is currently writing back home. Right now, space agencies are focused on steps, not leaps. The Artemis program aims to return humans to the moon and establish a semi-permanent presence there. Mars is the next great ambition, a world close enough to reach in months instead of years. In this unfolding roadmap, Saturn is not forgotten, but it is farther down the table of contents, a later chapter in the book of human exploration. On paper, Saturn already has its future visitors. NASA is preparing Dragonfly, a rotorcraft that will leap across the dunes of Titan, Saturn's largest moon. Titan is not just another icy rock, it is a world with lakes and seas, not of water, but of liquid methane and ethane. It has rain, clouds, and a thick nitrogen atmosphere, more like a frozen analogue of early Earth than any place we've yet found. Dragonfly is scheduled to launch in the mid-2030s, arriving in the early 2040s, depending on trajectory and planetary alignment. It will not carry humans, but it will carry our curiosity further than any footsteps could for now. Other mission concepts have been drawn and redrawn on whiteboards and in technical papers. Orbiters to map Saturn's rings in unprecedented detail, submarines to swim through Titan's hydrocarbon seas, landers to touch down on Enceladus and taste the fresh ice ejected from its subsurface ocean. The 2030s and 2040s are likely to be the era of Saturn's robotic renaissance, a time when new probes, if funded and approved, will follow in Cassini's wake and turn this distant realm from mystery into map. But if Saturn is so compelling, why is it not our primary destination? The answer begins with distance, but it does not end there. Mars sits relatively close to Earth, a world where days are only slightly longer than our own, where gravity is gentle but present, and where, at least in theory, habitats could be built, crops could grow, and people could one day live. It offers the possibility of being a second home. Saturn is different. Its surface is not a place at all, but a depthless storm. Only its moons offer solid ground, and even there, conditions are extreme. Titan is more than 1 billion miles away from Earth. Enceladus orbits an icy giant locked in darkness for most of its long year. From the perspective of mission planners, Mars is practice for living somewhere else. Saturn is a laboratory. NASA, ESA, and other space agencies must balance dreams with budgets, ambitions with risk. Mars offers a nearer-term pathway to learning how to keep humans alive beyond Earth for months or years at a time. Until we prove we can do that closer to home, a human voyage to Saturn remains not impossible, but impractical. Not denied, just deferred. Yet while national space agencies move methodically, another force is stirring in the background: private spaceflight. Companies like SpaceX, Blue Origin, and others are developing large reusable rockets, heavy lift systems, and eventually, spacecraft designed to ferry humans to the Moon and Mars. Their focus is near-term and nearer space. But every booster that returns to a landing pad, every engine that can be reignited without rebuilding from scratch, nudges the cost of spaceflight downward. Cheaper access to orbit changes everything. It makes larger missions feasible. It allows more ambitious payloads, more daring trajectories, more frequent launches. In this way, private space companies may not be the ones who first propose a human voyage to Saturn, but they may be the ones who accidentally make it possible. Imagine a future where building a ship large enough to carry humans, life support, radiation shielding, and fuel for a decade-long mission is no longer a once-in-a-generation gamble, but simply another engineering challenge. Private infrastructure, tankers in orbit, fuel depots near the Moon, modular habitats tested around Mars, could someday become the scaffolding upon which a mission to Saturn is quietly assembled. Before we can think about sending people to the rings, certain milestones must fall into place. We will need reliable deep space habitats where crews can live, work, and stay healthy for many years at a time, not just months. We will need advanced propulsion systems, high-efficiency ion drives, nuclear electric propulsion, or even nuclear thermal rockets to shorten the travel time and reduce the long isolation that such a journey demands. Radiation protection will need to evolve from walls and shielding into complete strategies for living in a universe constantly bathed in high-energy particles, storm shelters, magnetic fields, or materials we have yet to invent. Most of all, we will need experience. Long-duration missions to Mars and back. Habitats that function for decades without resupply from Earth. Closed-loop life support systems that recycle air and water with near-perfect efficiency. Saturn will not be our first test. It will be the exam we take after we have already passed many others. If our robotic explorers are the scouts of this future, the 2030s and 2040s will likely see them take bold new steps. Dragonfly on Titan. Perhaps a dedicated Enceladus orbiter to fly through its plumes and search for the chemistry of life. Maybe, if we choose, a new flagship orbiter to watch the rings slowly evolve, to measure their age, to catch their faint, frozen rain as it falls back into the planet. These missions will not carry astronauts, but they will carry questions. Is there life, or the chemistry that could lead to it, hidden in Titan's lakes or Enceladus's ocean? Are there energy sources, organic molecules, and stable environments where biology could thrive? Saturn itself may be forever beyond our touch, but its moons are like scattered laboratories, each one offering a different experiment in what worlds can be. In many ways, the moons are the true destinations. Titan, with its thick air and low gravity, could be a place where humans, one distant day, walk in heavy coats while methane rain falls quietly around them. Where aircraft drift lazily through a sky so dense that flight becomes easier than on Earth. Enceladus, with its water-rich geysers and hidden ocean, is a natural candidate for research stations if we ever learn how to build them gently enough not to disturb potential native life. So when might our own footsteps join those of our robotic proxies? If we project forward, cautiously, we can sketch a timeline written not in certainty, but in possibility. The mid-21st century may see regular human missions to Mars, crews staying for years at a time, rotating between Earth and the Red Planet. The infrastructure required to support those journeys, refueling depots, space tugs, long-lived habitats, will mature over decades. Advanced propulsion systems, may shrink the outer solar system from a multi-decade odyssey to something just barely within human tolerance. If all these pieces fall into place, if humanity chooses to continue outward rather than turn inward, then the first serious discussions of a human mission to Saturn might emerge in the late 21st or early 22nd century. Not as science fiction, but as ambitious policy. A mission measured not in a presidential term, but in generations. Human boots pressing into the orange sands of Titan may belong to people not yet born, living in a time when Earth's night sky is already threaded, with traffic between worlds. If we must assign a century to this vision, the 2100s or even 2200s are a plausible home for it. Not soon, not never, simply later. In the end, the timeline for humans at Saturn is not dictated by technology alone, but by choice. By whether we decide that crossing 1 billion miles of space to stand beneath a dim, far-off sun is worth the time, the risk, and the waiting. For now, robots will be our eyes and hands in the Saturnian system. They will hover above lakes of methane, taste the spray of hidden oceans, and watch the shadows sweep across the rings. And one quiet night, perhaps centuries from now, as someone stands on Titan and looks up to see Saturn's rings arching overhead like a frozen rainbow in the sky, they may wonder how long it actually took us to get there. Not in years of travel, but in centuries of dreaming. By the time we arrive at Saturn, years have passed. With the technology we have today, it would likely take 6 to 7 years to get here. With more advanced propulsion, powerful ion drives, nuclear systems, or other emerging concepts, that journey might shrink to 3 or 4 years. In human terms, that is a long wait. In cosmic terms, it is the blink of an eye. As we drift above Saturn's glowing rings, the original question lingers in the quiet of the cabin. How long would it actually take us to reach this world? We have our numbers now. But somewhere along the way, the meaning of the question changes. It is no longer just about calendar years or kilometers per second. It is about what those years represent. To travel to Saturn is to step outside the rhythm of daily life and into the tempo of the cosmos. We measure our days in alarms, meetings, and sunsets. Out here, time is measured in orbits, in gravity assists, in the slow unfurling of trajectories that were calculated long before the engines ever ignited. A 6-year cruise to Saturn forces us to confront a different kind of patience, the patience of a species just beginning to test the edges of its own horizon. The distance to Saturn is also a mirror, reflecting who we are becoming. Every mission that takes years to arrive is a declaration that humanity is capable of thinking beyond a single election cycle, beyond a single career, even beyond a single lifetime. Engineers plan missions they will never see completed. Scientists study data gathered by spacecraft launched when they were children. Time, in space exploration, is a relay race. Each generation hands the baton forward. That is why this question matters for our future as a spacefaring species. If we can accept that reaching Saturn takes years, we open the door to journeys that take decades. To Uranus, to Neptune, to the Kuiper Belt, where ancient ice remembers the birth of the solar system, and eventually to missions that leave the sun's comforting glow behind altogether. Interstellar travel does not begin with faster-than-light drives. It begins with a willingness to start a journey knowing that others may be the ones who finish it. The path to Saturn reminds us that progress is not always about raw speed. It is about choosing when to be patient and when to be bold. We refine our chemical rockets, We experiment with nuclear propulsion. We dream of sails driven by starlight or beams of energy. Some ideas will fail. Some will seem impossible, until, quietly, they are not. Innovation in spaceflight is less like a sudden revolution and more like the slow, steady tightening of a spiral, drawing us ever farther from home, yet ever deeper into understanding. And in that understanding, perspective grows. From Saturn, Earth is a speck hidden in the glare of the sun, a world where all our histories, our conflicts, our languages fit into a single pale point of light. Watching that tiny dot from a spacecraft window, the years spent crossing the void no longer feel like a delay. They feel like the price of a deeper vision. If you've made it this far in the journey, you are part of that vision too. If you enjoyed traveling to Saturn tonight, please take a moment to gently like this video, subscribe to the channel, and let this kind of long-form exploration keep reaching more people. In the comments, I'd love to know, where in the world are you listening from right now? A city, a country, or just under the stars is perfectly fine. If you'd like to support the channel more directly, you can also consider joining as a YouTube member. It's completely optional, but it helps make more videos like this possible. More slow journeys through deep time and deep space, shared with you wherever you are. For now, as Saturn's rings drift past and the stars sharpen against the darkness, we remember. The destination gives the journey a goal, but the journey gives the destination its meaning. Whether it takes 7 years or 3, every mile between Earth and Saturn is part of the answer.